Welcome back to Integral Calculus. In this video, I want to review the integral. The naming has always seemed a little bit odd. This video series is called Integral Calculus, but I expect that you've already been exposed to the integral in a previous course, like my video series on differential calculus. There's a historical reason that the timing seems odd like that. At one point in the past, calculus was a 4-semester sequence of 3 credit courses where all of integration showed up in the same semester. But as a concession to the fact that you need to understand calculus in order to do much of anything in physics and engineering, we have accelerated things greatly and compressed it down to a 3-semester sequence instead. And so this breaking point of integration happens right between courses, where an entire course on just integration would make a ton of sense. But without that, you would need a graduate degree to do anything at all in engineering instead of needing a graduate degree in order to be an engineering supervisor. So I guess on the balance, it's something that's better. Anyway, enough rambling. Let's remind ourselves what we are talking about here with the integral. First of all, there's 3 vocabulary ideas that are very closely related. Of antiderivative, indefinite integral, and definite integral. All right, let's consider a function. Let's consider a very simple function. F of x equals 2x minus 1. As functions go, they don't get that much simpler than that one. All right, the antiderivative, the indefinite integral, and the definite integral are all things that we can determine based on this function. An antiderivative is any one function whose derivative is the original function. So for example, capital F of x equals x squared minus x. If you differentiate x squared minus x, you will be arriving at 2x minus 1. That is an antiderivative. But that's not the only possibility. If I call this f1 of x, I might also have big F2 of x, which is x squared minus x minus 9. If you take the derivative of x squared minus x minus 9, you will again end up at 2x minus 1. That's another antiderivative. And in fact, there are infinitely many such antiderivatives. But if you just need one, we call it the antiderivative. If you need a general expression for all of them, we call that the indefinite integral. The integral of f of x dx is the family of all of the possible antiderivatives. In this case, it would be x squared minus x plus some arbitrary constant of integration. If I pick c equals 0, I get big F1. If I pick c equals negative 9, I get big F2. If I pick something else, I'll get a different antiderivative. The definite integral is a little bit further removed. The fundamental theorem of calculus says that if we want to evaluate a definite integral, we can take any one of our antiderivatives, evaluate at b, take that same antiderivative, and evaluate at a and take the difference between them. So in this case, that's going to be 2 times b minus a. I'm sorry, I'm looking at the wrong thing. That's going to be b squared minus b minus a squared minus a. And pick values of a and b to get a particular definite integral, and you can go from there. Antiderivatives and indefinite integrals are probably the more interesting ones mathematically of the integration forms, but the definite integral is definitely the one that is most important in the sense of applications. You may remember from your previous mathematics course that the definite integral gives the area under the curve y equals f of x between those points. So if my curve here is y equals f of x, my area here is the integral from a to b of f of x dx. A lot of the struggles that students have in this course is not paying close attention to which kind of thing is being asked for. In most of the application problems we look at in this course, you're going to end up needing a definite integral because a numerical value as your solution tends to be the most useful thing. In the more generalized, more abstract problems, integrate this function, an indefinite integral is by and large going to be the thing that we are looking for. And there are definitely applications where the indefinite integral becomes important. Why am I saying definitely so much in this video? Sorry. There are applications where the indefinite integral becomes important. We will get to some of them in this course. But a lot of what we do in this course is going to be studying methods of integration. We're going to be looking for ways of finding that antiderivative in the first place. And then the last steps are just cleanup steps. If you have the antiderivative, the rest of it's really easy. All right, let me get my head out of the way. Let's go through a couple of quick examples. First of all, an indefinite integral. I don't want to be that thick. That's a little bit nicer. How about the integral x squared minus 9 dx? Well, this is just a polynomial, so we can go ahead and use the product rule. The integral of x squared, well, 2 plus 1 is 3, so that's going to be 1/3 x cubed. 9, well, that's 9 times x to the 0, 0 plus 1 is 1, so you'll get 9 over 1, which is 9, times x to the first, which is x. And then because this is an indefinite integral, we want the family of all possible solutions, which means I need to add a plus c at the end. If I want to take a look at a definite integral, how about the integral from 1 to 4 of 2 times the square root of x dx? Well, dealing with square roots with integrals, just like with derivatives, I tend to find easiest if I think about that as x to the 1/2 power. Then I can use the power rule. 1/2 plus 1 is 3/2. So we will have 1 over 3/2. And then we will have x to the 3/2 power. Then we have that 2 in front. But then we have to follow the fundamental theorem of calculus and evaluate this at each of the limits of integration. I think it's going to be useful here to clean up a little bit before we actually plug in. So 2 divided by 3 halves is 4 over 3. X to the 3 halves power is x times the square root of x, just simplifying that radical. And I wanted to do it that way because I know that the square root of 4 is 2, and the square root of 1 is 1. So we've got 4 times 4, which is 16, times 2, which is 32. And we've got 4 times 1, which is 4. And all told, my value there is 28 over 3. Here's one for you to think about. The integral from 0 to pi of sine of x. Take a couple of minutes, write out your solution to this one, and I'll see you in the next video.